Forget everything you know about the global energy crisis, because the solution may not be waiting in the stars, buried inside some distant asteroid, or hidden inside a futuristic reactor that has not been built yet. It may already be here, miles beneath the waves, in a world so dark, so pressurized, and so violent that it looks less like Earth and more like the surface of another planet. Scientists have been studying volcanic ridges deep beneath the ocean, and what they are finding is not just another strange geological feature. They are uncovering a thermodynamic secret, a natural energy system powered by the heat of the planet itself, where freezing seawater and superheated volcanic fluid collide in one of the most extreme environments on Earth. These places are not silent, they are not dead, they are pulsing, reacting, and releasing energy constantly, like hidden planetary batteries scattered across the deep seafloor. There is a relentless kinetic force moving along the jagged ocean floor, flowing through cracks in the crust, rising through volcanic wounds, and erupting into the black water with enough heat and chemical intensity to support entire ecosystems without sunlight. These hydrothermal vents are not just geological anomalies. They are engines of oceanic physics, places where heat, pressure, minerals, and water combine into a natural power system that has been running for millions of years. Long before humans burned coal, drilled oil, split atoms, or covered deserts with solar panels, the deep Earth was already generating energy in darkness. The question now is whether we can understand it well enough to use it. Deep within the crushing darkness of our oceans lies a jagged volcanic world, harboring enough energy to completely change how we think about power. Along the mid-ocean ridges, where tectonic plates slowly pull apart, seawater slips into cracks in the crust and begins a journey into the planet. It sinks downward, heats up near magma chambers, dissolves minerals from the surrounding rock, and then blasts back upward through vents as superheated fluid. When that fluid meets the near-freezing ocean, the result is a massive thermal gradient, a violent difference between hot and cold, between pressure and release, between chemical imbalance and equilibrium. And wherever there is difference, there is usable energy. This is the part that makes the deep ocean feel almost impossible. At the surface, we are used to thinking of energy as something visible: sunlight striking a panel, wind turning a turbine, fire burning fuel, water spinning a dam. But down there, where no sunlight reaches, energy looks different. It does not arrive from the sky, it rises from below. It comes from Earth's internal heat, from radioactive decay inside the planet, from leftover heat from Earth's formation, and from the constant movement of tectonic plates. It is not weather dependent. It does not care whether it is day or night. It does not stop because clouds arrive. It keeps moving because the planet itself keeps producing heat. To picture this world, imagine descending through the ocean in total darkness. At first, the water seems empty, blue, and familiar, but as you go deeper, the sunlight begins to fade. The bright surface disappears above you, replaced by a dim twilight, then by complete blackness. Pressure begins to build from every direction. At 1,000 meters, the ocean is already pressing with terrifying force. At 2,000, 3,000, 4,000 meters, the weight of the water becomes almost unimaginable. A human body would not survive here without protection. A submarine has to be engineered like a small spacecraft, not because it is leaving Earth, but because it is entering one of Earth's most hostile frontiers. Then, in that darkness, the seafloor appears. It is not a smooth plain. It is fractured, volcanic, uneven, and alive with geological movement. There are ridges, cracks, chimneys, mineral towers, and fields of black smokers rising from the seafloor like industrial smokestacks built by the planet itself. From these chimneys, dark clouds pour into the water. Not smoke exactly, but mineral-rich fluid so hot and chemically loaded that it turns black when it hits the cold ocean. The scene looks like a factory from another world, except there are no machines, no wires, no engines, and no human operators. The machinery is geology. This is why scientists often think of these environments as natural batteries. A battery does not create energy from nothing. It stores energy in separation, in difference, in chemical imbalance. When the circuit is completed, energy flows. Hydrothermal vents work in a similar conceptual way. The Earth separates heat from cold, deep minerals from ocean water, volcanic chemistry from seawater chemistry, and when those forces meet, energy is released. The vent is not just a hole in the ground, it is a connection point between two worlds, the cold ocean above and the hot interior below. The most obvious energy source is heat. A hydrothermal vent can release fluid at temperatures that may exceed 350 or even 400 degrees Celsius, while the surrounding seawater remains near freezing. That temperature difference is enormous. In human technology, temperature differences are used all the time to generate power. Steam turbines work because heat creates motion. Even power plants, whether fueled by coal, gas, nuclear reactions, or geothermal heat, are often built around the same basic principle: use heat to create movement or electrical flow. So when scientists look at hydrothermal vents, they are not just seeing strange underwater chimneys. They are seeing a naturally occurring heat engine. The planet is supplying the hot side. The deep ocean is supplying the cold side. The gradient is already there. The challenge is how to place technology inside that gradient and extract useful electricity without being destroyed by the environment. One possible method is thermal electronic generation. Thermoelectronic materials can convert temperature differences directly into electricity. Place one side of the device near a hot source and the other side near a cold source, and the movement of heat through the material can create voltage. The appeal is obvious: no spinning blades, no massive turbines, no combustion, no fuel delivery. In theory, a deep-sea thermoelectronic generator could sit near a vent and use the contrast between superheated vent fluid and cold seawater to produce electricity. But theory is much cleaner than reality. The deep sea is brutal. The fluids coming out of hydrothermal vents are not just hot, they are corrosive, mineral-rich, chemically reactive, and physically unstable. They can clog equipment with mineral deposits, they can damage metals, they can change over time as vents shift, weaken, or collapse. The terrain itself is volcanic and unpredictable. Building a generator there is not like building one beside a river. It is like building inside a boiling chemical storm, in total darkness, under crushing pressure, miles from the nearest repair crew. Another possible method involves the kinetic force of vent fluids. When hot fluid shoots from the seafloor, it moves with energy. In principle, that movement could be used to turn tiny turbines or mechanical systems. But again, the problem is durability. Anything with moving parts becomes vulnerable. Turbines can jam, blades can corrode, minerals can build up, pressure can distort components. What looks simple on land becomes extremely difficult under 4 kilometers of ocean. There is also chemical energy. This may be the most fascinating part, because life has already solved part of the problem. Around hydrothermal vents, entire ecosystems exist without sunlight. On the surface, almost all food chains begin with the sun. Plants use photosynthesis. Animals eat plants or other animals. Energy moves through the biosphere from sunlight. But at hydrothermal vents, life is built on chemosynthesis. Microbes use chemical reactions, especially involving sulfur compounds, hydrogen, methane, and other reduced chemicals, to produce energy. These microbes become the foundation for entire communities of tube worms, clams, shrimp, crabs, and other creatures that look almost alien. That means the vent is not only a geological power source, it is a biological power source. It proves that life can build an ecosystem from chemical gradients alone. Scientists study these organisms because they reveal how energy can be extracted from chemical imbalance in ways that are efficient, resilient, and self-sustaining. Some researchers are interested in bio-inspired energy systems that mimic microbial processes. Instead of forcing the deep ocean to fit our existing machines, we may learn from organisms that already mastered the environment. This is where the story becomes bigger than electricity. Hydrothermal vents change the way scientists think about life itself. Before their discovery, many people assumed that complex ecosystems needed sunlight. But vents revealed that life could flourish in darkness as long as energy was available in another form. That discovery had implications for Earth's history, for the origin of life, and even for the search for life beyond Earth. If life can survive around deep-sea vents here, then maybe similar life could exist beneath the icy crust of moons like Europa or Enceladus, where subsurface oceans may interact with warm, rocky interiors. So when we talk about deep ocean energy, we are not talking about a simple fuel source. We are talking about one of the fundamental energy systems of rocky planets. Heat from the interior moves outward, water circulates through cracks, minerals dissolve, chemicals react, life adapts, energy flows. This may be one of the oldest forms of power on Earth, older than human civilization, older than agriculture, older than forests, maybe even connected to the earliest chemistry that helped life begin. But can it power civilization? That is the question that turns wonder into engineering. The energy is real, the gradients are real, the vents are real, but usable power requires infrastructure. A generator on the seafloor is only the first step. Electricity would need to be transmitted upward or stored locally. Cables would need to stretch from the deep ocean to the surface, then possibly back to land. Maintenance would be expensive and dangerous. Storms, currents, saltwater corrosion, tectonic movement, and biological growth would all create problems. The ocean is not just deep, it is active. Fossil fuels are stored sunlight from ancient life, compressed over millions of years and burned in a few centuries. They are dense, convenient, and powerful, but they release carbon that had been locked underground. Hydrothermal energy is different. It is not based on combustion. It does not require digging up ancient carbon and burning it. It comes from heat already moving through the planet. If captured carefully, it could provide steady power without the same emissions profile as coal, oil, or gas. Compared to solar and wind, deep ocean hydrothermal energy has another advantage: consistency. Solar power fades at night and changes with weather. Wind power depends on moving air. Both can be extremely useful, but they require storage, grid management, and backup systems. Hydrothermal vents are not affected by clouds or calm days. They are closer to baseload energy, meaning they could, in theory, provide continuous output. That is why the idea is so attractive. A clean energy source that runs all the time is one of the hardest things to find. But then comes the ethical problem. Hydrothermal vents are not empty industrial sites waiting for humans to arrive. They are living ecosystems. Many vent species exist only in specific regions. The best version of this technology may not involve covering the seafloor with generators. It may involve learning from the deep ocean and applying those lessons elsewhere. That is where enhanced geothermal energy becomes important. On land, geothermal systems already use Earth's internal heat to generate electricity. Traditional geothermal plants work best in places where heat is close to the surface, such as volcanic regions. But enhanced geothermal systems aim to expand that potential by creating or improving underground reservoirs where water can circulate through hot rock. In a way, they imitate the same basic process that happens naturally at hydrothermal vents. The deep ocean may therefore serve as a model. It shows what happens when water, heat, pressure, and fractured rock interact at planetary scale. By studying vents, scientists can better understand fluid circulation, mineral buildup, thermal exchange, and chemical reactions. Those lessons could improve geothermal energy on land, where infrastructure is easier to build and maintain. The deeper lesson is that energy is not always where we expect it to be. We look upward and imagine solar farms in space. We look outward and imagine mining asteroids. We look forward and imagine reactors that have not yet been perfected. But sometimes the future is hidden below, in ancient systems that have been running long before we knew how to name them. The ocean floor is not just a boundary, it is a gateway into the machinery of the planet, and that machinery is still operating. So the next time people talk about the future of power, the answer may not only be above us, shining in the sky. It may be below us, hidden beneath miles of black water, rising from volcanic scars in the seafloor, waiting inside the temperature difference between fire and ice. Because deep beneath the ocean, Earth is not silent. It is working, it is moving, it is producing energy in the dark. And we are only beginning to understand how much power has been hidden there all along. I post videos that break down how reality actually works from your brain to your body to the world around you, so if that sounds interesting, subscribe and I'll see you in the next one.